Hello, welcome to our final project, predicting ramen ratings. This is by me, David, and Allison, and Phil.
Okay, so the problem we're tackling is predicting the ratings of different instant ramen products based on a couple of different features. So our analysis focused on getting this data set to work for different types of algorithms. So uh, the data set had mainly categorical features, so we had to try to convert those to continuous in order for them to work for regression algorithms. So we chose linear regression and k-nearest neighbors for those, and then for classification, we chose naive Bayes. We're hoping to be able to achieve good accuracy across all the different models. Um, yeah. So the data set. The data set is pulled from the ratings from this website called the Ramen Rater, where this guy tries a bunch of different ramens and gives a rating to them. Uh, the data set has 2,500 rows and there's 6 columns. Review number, which is not relevant for us. Brand, variety, which is the product name. Style, so pack or tray. Country, which is country of origin. And rating in stars, which is what we're trying to predict. As you can see, it's all the features come down to categorical, and a lot of the categories have high cardinality. So brand and variety have many words per feature value, and in contrast, style has really low cardinality. It has the 3 categories. We had to reconcile that.
Alright, so our approach for getting data to work with these algorithms. So, the first thing we need to do is pre-process the data. So, we converted the categorical features to continuous features using a frequency sum of how often the words appeared in the data set. And we used this conversion for linear regression and KNN. We rounded the star ratings that had contained flip values of like 3.5, 3.25. We made them integers and nice whole round numbers for a discrete classes of 0 through 5. We built 3 different machine learning models using the ramen data set to evaluate their performance. To evaluate their performance, we use mean absolute percent error. The 3 algorithms we used were linear regression, using both the closed form solution and the gradient descent variations. We used KNN, and to evaluate KNN, we used squared Euclidean distance, and we used multimodal naive Bayes for our 3rd algorithm. So prior work, there's a lot here, so I'm just going to go over some of the highlights, but for this we wanted to look at both research pertaining to predicting ratings of some sort and research comparing the 3 different algorithms head to head. So for predicting ratings, we found some prior work on predicting product ratings using linear regression, and it found that linear regression measured with mean absolute error only had an effectiveness of between 0.6 and 0.7 on this sort of problem. Comparing naive Bayes to KNN, KNN outperformed naive Bayes in both of these experiments listed, however, not always by that big of a margin, and sometimes KNN was shown to be worse performing the more noisy, statistical, insignificant data there was, so both of these studies came with that sort of caveat. We also looked at KNN versus linear regression, where these 2 models were predicted to make predictions on sales data from a German pharmacy chain, and they performed comparably, but linear regression performed slightly better. And with naive Bayes versus linear regression, there was a study that compared these 2 models, and for the data they were using, all the variations of linear regression outperform naive Bayes on these sort of problems, except for global linear regression, which in certain circumstances performed on par with naive Bayes.
Okay, so for the pre-processing, we first had to convert the features from three categories to continuous values. So for every feature, we calculated the frequency of every word we saw and divided it by the total number of words to get this kind of frequency percentage. So for the features with multiple words like brand and variety, we had to do the sum of the frequency percentages of every word that appeared. And then for country, because it wouldn't make sense to split up country names, we just had each country had its own frequency percentage, and that was just assigned. For style, because of the low cardinality, there are only three categories. We kept it as just a raw frequency. As Dave mentioned, we rounded the ratings into discrete classes for 90 days, and then we did some standard pre-processing. So we split the training set, validation set as usual, and the training set was 1,701 samples, and the validation set was 836 samples. So then we de-scored the continuous features and added a dummy variable for linear regression. KNN. So working with the data set, we quickly realized that the class 4 stars appeared a lot more than all the other classes. So this really messed up the performance of K nearest neighbor. It was always predicting around 4 because that was what I was seeing from the data set. I plotted the performance of K and N in comparison to different Ks that I assigned, and I did 1, then 100, 200, so increments of 100. And you can see what happens to the map value. For K equals 1, unsurprisingly, map is really bad, 0.55. And the best, which is 1700, the map is 46%, which is, despite being the best, it's fairly meaningless because that's this entire training set. So it's essentially just predicting the mean of the training set. And yeah, basically KNN performed very poorly.
Next up, we use linear regression, and as mentioned before, we use both direct method and gradient descent, and we evaluated the MAPE and saw that even though it was better than random, both of these versions were quite susceptible to overfitting problems. So any future work would need to take into account dealing with overfitting when trying to use this data set. The direct solution had a very stark difference between training and validation of 0.25, 0.2 for the training and 0.5 for the validation. Gradient descent was a little closer at 0.34 for training and 0.41 for validation.
Our final and most successful method was naive Bayes. We took each of the features, converted it into tokens, and analyzed these tokens using Bayesian logic. In order to balance the classes, we did try using oversampling. However, it actually increased the MAP, so perhaps a more sophisticated method would be useful. This performed well on training with a MAP of about 0.1 and generalized fairly well as well. This good performance is probably because of naive Bayes' aptitude for bag of words features, and this classifier could perhaps be improved by introducing features that show conditional dependence like bigrams. So in the end, our best performance was from naive Bayes with an MAP of 0.3116. KNN performed the worst at k equals 1 with a MAP worse than a literal random classifier. All the models could benefit from class rebalancing. However, all of them perform better than random, KNN with a k larger than 1. KNN was impacted most by class imbalance, and both the linear regression models suffered from overfitting. However, naive Bayes performed well on this language dataset.
Okay, future work. So we had a lot of ideas of what we could do to improve things. All the models could probably improve or at least have more of an even playing field with rebalancing the classes, so we could do some kind of upsampling, or there are other ways to generate data from small data sets. We could improve KNN and linear regression because they're the worst. They have the worst, a little bit worse performance. Uh, we could use different methods to convert the features to continuous values, maybe something that's more meaningful than that frequency percentage sum. Some ideas are like assigning uh, sentiment analysis cores to the different features, or doing some other kind of natural language processing techniques. Um, Also, to improve their performance, we could do some kind of like model variant. So we could do like locally weighted regression, or KNN with a kernel instead of a squared Euclidean distance, because working in a higher dimension, or implicitly working in a higher dimension, might give KNN more information. Um, Other extensions include we could implement hybrid algorithms, as some of the prior work did, or if maybe we're trying to force it to be a regression problem wasn't a good idea, and we could try other algorithms to see how they did instead.
All right, thank you for listening. Thank you for teaching this course, Dr. Burlick. That's our presentation.